So we're going to talk about what happens when your body goes into an elevator, and there are portions of an elevator ride where you feel the movement. You feel heavier or you feel lighter. Now, before we can even talk about the forces in play and what's happening there, we do have to distinguish between the difference of mass and weight. Okay? Mass, again, your chemistry teachers talk about how much matter, how much stuff, how many molecules are present of a given element. And so mass is a measure that does not change whether we are on Earth or on the moon. If I have 1 kilogram, it's 1 kilogram of matter. Whereas weight, that's a different story. Weight is talking about the force of gravity acting on the object. So when we say force of gravity, we say weight, and a lot of the problems in this unit will talk force of gravity or weight. Know that they're the same thing, okay? But anyways, weight is talking about the amount of pull of gravity acting on an object. And so we measure that in newtons. Big way to distinguish between the two in word problems. If you get something in kilograms, that means it's a mass. If you get something in newtons, you means it's a force. And if it's talking about the pull of gravity or the weight, it's talking about this, okay? So now that we've talked about it, we do have to actually have conversation about what's happening inside of an elevator when you are moving. So in an elevator, if you're moving, okay, you're going to feel movement, obviously. You're going to feel heavier or lighter. But when you're still on a scale, okay, this is what your force diagram would look like. Your normal force and your force of gravity are equal and opposite because your velocity is 0, your acceleration is 0. But like I said, when we are standing on a scale and we're accelerating either up in an elevator shaft or down in an elevator shaft, we feel different. The force normal is what changes. And I want to show you guys a graph of what that looks like. So here's a graph of someone standing in an elevator when it's at rest, and then all of a sudden they lose weight somehow. Okay, well, they're not actually losing mass. Their normal force is going down. They feel lighter. This would probably be a graph of an elevator ride when you're at the top and all of a sudden the elevator starts moving down the elevator shaft. You feel lighter, and there it is acting lighter. Now you're moving down again at a constant speed, and so your weight goes back to normal, or your force normal goes back to normal. And then at the bottom, when you stop, you feel heavier. Well, we can measure that feel heavier, and you actually get a larger normal force. The floor pushes harder on your body to stop you. So the reason I bring that up, and this is probably the biggest takeaway of this whole video, is that when you look at the normal force, that's what a scale reads, or reverse that. The scale is actually reading the normal force. Now, most of us have probably been on a bathroom scale at some point, and when you stand on it, your mass does not change no matter what. But if you bounce up and down, the scale, the hand will bounce like this if you're jumping up and down. And so we know that that's not your mass changing. That's the reading on the scale changing, which is your normal force. So back to elevator stuff. Okay, I showed you that graph of accelerating downward, so I guess I'll start with this one. Okay, so we're at the top of the shaft, we're standing still, we feel lighter, and then at the bottom of the shaft, then we stop and we feel heavier. So when we have a downward acceleration, that means we have a downward unbalanced force. So this would be what our force diagram would look like in general. Gravity can't change, normal force can, and so if you have a downward acceleration, that means your normal force gets smaller so that we can accommodate for a negative unbalanced force and therefore a negative acceleration. Now, these are the two scenarios in an elevator that you would feel lighter. You would have a lesser normal force. You would be accelerating down. That'd be like if you're at the top starting at 0 and moving down like the graph I just showed you. The other way that you could actually feel lighter and have a lesser normal force, if you're moving upward, positive velocity, upward, and you go to a stop at the top of the elevator shaft, you feel lighter. So again, force of gravity is larger than force of normal because we have that lighter feeling. Okay. Now on the other end of it, in an elevator, if you're accelerating up, say starting at the bottom floor at rest, okay, and you're moving up or you accelerate upward, you feel heavier. You feel heavier because your normal force is larger than your force of gravity. Your force diagram would look like this. Again, gravity can't change. And if you notice between my two diagrams, my force of gravity is the same. The one that's changing is my normal force. So I feel heavier. That means I have an upward unbalanced force. That means my normal force is larger. On the other end of it, if I'm moving downward and I slow to a stop, I feel heavier, and I therefore then have a larger normal force. Okay. When working through elevator problems, one of the main things that I suggest to students as they're learning this, think about what you would feel, and that will help you draw what your normal force should be in comparison to your force of gravity. So here's what I do want to do. I have an example problem, and this is actually from your packet worksheet worksheet 2, number 3. Okay, so this is talking about a student standing on a scale in an elevator at rest. He weighs 840 newtons. When the elevator rises, his weight doesn't increase. The force normal increases. So what he reads changes. So the scale says 1050 and then returns to normal. Okay, so we'll figure out what to do with that. And then when the elevator slows to a stop on the 10th floor, he drops his force normal. That feels lighter, 588 newtons. So we're not going to do motion math, so we can forget about that part. Okay, but we want to figure out the acceleration at the beginning and at the end. So I guess what I'm going to do is I'm going to start out by just drawing force diagrams. So at rest, at the beginning, he's standing still in the elevator shaft. So it tells us the force of gravity and the weight. Well, the scale reads 840. So we know what the scale reads is 840. And since he's at rest, we should also know then that these two are equal, meaning that our force of gravity is 840 newtons. Okay? So your force of gravity is your force of gravity. It's the same guy in the elevator. So it doesn't matter what the elevator is doing. The force of gravity acting on him when he is accelerating up, it's still going to be that 840. Okay? And then at the top, when it's accelerating downward, when he feels lighter, the force of gravity is still going to be 840. Okay. Again, I'm just working through force diagrams before I even try to find accelerations. I want to know the forces first because I know I'm eventually going to have to use FUMA to find accelerations. Okay. So the next part, I guess I would do, I'm just going to go back to my beginning one. If I have 840 newtons of force, I can also use this equation, force of gravity is mass times gravity, to solve for its gravity. So I'd have 840 is equal to mass times 9.8, which means his mass, if I do the algebra, ends up being something like 85.7 kilograms. So again, mass and gravity are different things. Mass is how much matter, gravity is pull of gravity on an object. Okay, so I think I have everything that I can get from this one. Obviously, the acceleration is 0 there because he's not moving. Okay. When we're accelerating up, we know that his weight increases to 1,050 newtons. So that means I have 1,050 newtons for my force normal. Okay. And so if I want to know what the acceleration is, I'm going to need to use FUMA, but before I can even do that, I need an unbalanced force. So I know that like this is bigger than this. Okay, so being that this is larger than this, my FU is upward, and I got to find it. So my unbalanced force is going to be 1050 minus 840. So the unbalanced force, based off of my force diagram, seeing that this pull is larger than that pull, my unbalanced force ends up being 210 newtons. And now that I have that, I can apply it to FUMA. Okay, so the unbalanced force is 210. The mass we found before is 85.7, and the acceleration is what we would be solving for. So again, dividing both sides by 85.7 to get acceleration by itself. The acceleration in that middle phase is a positive 2.45 meters per second squared. I apologize for how tight this is, but so that's essentially the way that we would do it. Now, the last part, acceleration is downward. We know that he feels lighter, so his normal force is going to be lesser. And they tell us it's 588. And so again, if I want to know the unbalanced force, it's going to be my downward force, the bigger one, 840, minus 588. And so doing math, the unbalanced force ends up being 252. And likewise that we did over here, we're going to use FUMA to solve for what the acceleration downward now is. And so the unbalanced force is 252. The mass we found before was 85.7. And then we would divide both sides by that to get an acceleration of, let's see real quick, so 252 divided by 85.7, 2.9
4. So we'll round that to 2. Okay. So ultimately, that's it. That's elevators. I guess big takeaway for you guys on this type of work. Couple things. One, the normal force is what the scale is reading. So when you're told the scale reads, or when you're told you feel, that's your normal force. Okay. In summary, 2, force of gravity is larger than force normal when you feel lighter. Force normal is larger than force of gravity when you feel heavier. And then lastly, know the difference between mass and weight. Mass is kilograms, how much stuff. It's a measurement of molecules. Weight, on the other hand, is talking about the pull of gravity on that mass. Hopefully that helps with elevators.